So, welcome to the next session of this next class of this session. So, we are discussing about the stability of the steady state. So, we in the last lecture we finished we have started the classification of the steady state, and we have discussed about the two steady states. One is the unstable node, another is the stable node. Now, in this class we will finish the classification of the steady state, and further we develop our theory. So, for the stability analysis. So, next steady state that we talk about is the saddle point, saddle steady state. So, let us see what a saddle is. At this steady state, some eigenvalues are positive, some eigenvalues are negative, and we have real, first condition is for the saddle we have real valued eigenvalues. Secondly, some lambdas are positive and some lambdas are negative. So, the saddle is always unstable. So, if you look into the phase plane plot for the saddle, it will look something like this. So, in one steady state branch, you will be, let us say this is u2 and this is u1. So, lambda 1, lambda 2 are two eigenvalues, corresponding eigenvectors are u1 and u2. Now, in this case any disturbance will decay. So, lambda 2 is negative, and along this eigenvector and along this eigenvector u1 any disturbance will grow in time. So, therefore, lambda 1 is ever positive. So, this is case of saddle. Saddle is basically a steady state where at least some of the eigenvalues are positive and some of the eigenvalues are negative. Next steady state we will be talking about is called a stable focus. Now, in this case the eigenvalues are imaginary, and they are in the form of p plus minus I q. So, in case of real values of lambda 1 is less than 0 and real value of lambda 2 is also less than 0, then we call this focus is a stable focus. So, trajectory. So, basically if you look into the phase plane plot, it will be the steady state is here. So, whenever you will start from, it will spiral coming to this steady state. So, trajectory is spiral towards steady state. Steady state, and from where it will be spiraling, that will be depending on the initial conditions. Okay. So, it will be spiraling in that particular path, and as you have seen that it contains an imaginary part, it will be the solution, in the deviation variable or part out variable will be in the form of sine and cosine function. So, it will be having a spiral nature towards the steady state or away from the steady state. So, in the case of real values of lambda 1 and lambda 2 are negative, then we will be landing with a stable focus, and focus will happen only in case of imaginary complex. So, it is not imaginary, it is basically complex and complex conjugate. So, eigenvalues are complex conjugate. Okay. So, then we will be having a focus. So, the condition for having a focus is that complex conjugate eigenvalues must occur, that is number 1, and secondly it will be a stable focus if the real values of the eigenvalues are negative, then you will be having a stable focus. In case of unstable focus, the lambda 1, lambda 2s are complex conjugate, and they are in the form of p plus minus I q, and real values of lambda 1 and lambda 2 are always greater than 0. Now, if you look into the phase plane plot x 1 and x 2, then in this case the steady state, the focus will be unstable and it will be diverging away from the steady state. The deviation or perturbation will be diverging away from the steady state. Therefore, now in case of the trajectories, whatever we are talking about in the phase plane plot, these trajectories are equivalent to magnetic lines of force or the streamlines in a fluid flow. And therefore, no two trajectories will intersect each other at any point in the phase plane. No two trajectories intersect each other at any point of phase plane. So, that is a typical property of the trajectories in the phase plane plot. And next we look into the bifurcation theory and the actual theory for the stability analysis in any chemical engineering system. So, next we define what a stability is. With this background, we are able to take up the stability analysis using the bifurcation theory, which is also known as the linear stability analysis. So, stability of a state is determined, is evaluated by examining if a small perturbation about that steady state grows or decays in time. That is the definition of the stability of a particular state. Next, we talk about if basically for a steady state you just give a perturbation. If that perturbation grows in time, it becomes an unstable steady state. If the perturbation decays in time, it is a stable steady state. Next, we look into the bifurcation theory. This is also known as the linear stability analysis. So, it has into if the parameter so basically in the bifurcation theory says that we have several system parameters. System parameters are nothing but combination of operating variables operating variables and inherent system properties. Inherent system properties. Okay. So, that is the system parameters, and it says that if parameter changes, if parameters change, a new solution is generated. Now, that we have to test whether the new solution is stable or unstable. In other words, one can get the bound on the parameters for where the solution or the steady state is always stable or always unstable, or you can get the combination of the parameters or the conditions on the parameters where the solution moves from stable to unstable region. So, that those, if you want to operate under the stable steady state, those conditions have to be avoided. So, what a linear stability analysis or bifurcation theory does? Bifurcation theory has two functions. First one, it discusses stability. Stability subject to very small fluctuations. Discusses stability of solution. It calculates the points or the parameters, conditions on parameters where stability changes. Okay. One also get a boundary of unstable region or stable region. One can get a boundary of stable or unstable region. Now, we just take up an example, and the example I preferred is that the example whatever we have done with the earlier with the in context of whenever we have discussed about the contraction mapping, the CSTR problem. So, let us take up the example of CSTR problem, non isothermal CSTR. So, if you look into the unstable solution, the variation is something like this. If B is greater than 4 into 1 plus beta, then this is DAI ignition, this is DAE Damkohler number extinction. So, so DAE and DAI are called the bifurcation point. If we change the if we slightly shift the Damkohler number from DAE or DAI, you will be getting a new steady state. either in the upper half branch or in the lower half branch. So, if we across the bifurcation point the solution changes. So, across bifurcation points solution changes. So, if we write down the governing equation of this system, things becomes clearer and we can go further with the analysis. So, for mass balance will give you dC dt is equal to minus C plus dA 1 minus C e to the power t, and this is function of C and T. Concentration and temperature, this is non-dimensional concentration, is basically conversion and temperature. So, dt dt is nothing but minus 1 plus beta T plus B dA 1 minus C e to the power t. This will be some function of function g of concentration and time. So, at the steady state we have 0 is equal to function of CSS and TSS, and 0 is equal to some function the g of CSS and TSS. Now, the steady state will be obtained by solution of this equation. Solution of these two equations will give you the steady state. Gives the steady state values of CSS and TSS, but the point is this cannot in this particular form these two equations cannot be solved analytically. So, one has to take recourse to the nonlinear so because these two equations are nonlinearly connected, and therefore, one has to take the iterative technique, maybe a Newton-Raphson technique will be suitable. So, some kind of iterative technique can be adopted to solve these two equations, because subject to given a set of the parameters, because they are not linear in nature, and one can take recourse to the Newton-Raphson technique numerically to solve this set of equation in order to get CSS and TSS the steady states. Now, the question is whether the steady state CSS and TSS they are stable or unstable. So, what we do? We write C as a function of T as CSS plus C star T, and T as a function of time as TSS plus T star T. So, this star indicates the perturbation about the steady state. Perturbation about the steady state. Now, we write the governing equation in terms of the perturbed variable C star and T star and see what we get. So, if we really do that, we will be getting dC star dt is equal to function of CSS plus C star and TSS plus T star, and dt star dt will be function of CSS plus C star and TSS plus T star. Now, again we have the we use the Taylor linearize the problem, linearize the equations using Taylor series expansion. and retaining the first order term and neglecting the higher order term, assuming the deviations are quite close to the steady state. So, we have a linearization f of c t will be about the steady state. Okay. This has to be done about the steady state. So, f of c t will be nothing but f of c s s and t s s plus del f del c about the steady state c s s t s s c minus c s s plus del f del t about the steady state t minus t s s, and t minus t s s is nothing but t star, c minus c s s is nothing but c star. So, therefore, we will be getting the similarly we can expand a Taylor series expansion with respect to of g of c and t about the steady state, and what we will be getting is that dt star dc star, okay, we will be getting dc star dt is nothing but f of CSS TSS plus del f del c about the steady state times c star plus del f del t about the steady state times t star, and dt star dt will be is equal to g of CSS and TSS plus del g del c steady state c star plus del g del t steady state t star. Now, at the steady state this will be equal to 0, this will be equal to 0. So, we have d c star dt is equal to f of f c, we just call this as f c c star plus f subscript t t star and d t star dt is equal to g of c c star plus g of t t star. So, what is f c? F c is nothing but del f del c at the steady state, f t is del f del t evaluated at steady state, g c is del g del c evaluated at steady state, g t is del g del t evaluated at the steady state. So, therefore, in a compact notation, matrix notation, these two equations can be written as du dt is equal to a u, where u being a vector comprising of c star and t star, and a is the Jacobian matrix that is f of c f t g c g t, which are nothing but this derivative with respect to steady state evaluated at the steady state, and that forms the Jacobian matrix. So, we are basically having an equation in the form of du dt is equal to a u, and assume the let us assume the solution in the form of so this variable u, the vector u is nothing but it is made of elements which are in the form of perturbed variables. So, assume the solution in the form of c star is c hat e to the power sigma t and t star is t hat e to the power sigma t. So, if we put all this in this equation, so this becomes c hat. So, we put d c star dt is equal to f c c star plus f t t star. So, d c star dt will be c hat sigma e to the power sigma t is equal to f c c hat e to the power sigma t plus f t t hat e to the power sigma t, and you will be having this C hat sigma, that e to the power sigma t will be cancelled out, C hat sigma as F c C hat plus F t t hat, and from the other equation d t star d t is equal to G c C star plus G t t star, we will be getting t hat sigma is equal to G c C hat plus G t t hat, and in the compact notation you can write this equation as sigma u hat is equal to A u hat, and the here u hat is nothing but the vector comprising of the elements as C hat and T hat. So, they basically you will be getting A u hat is equal to nothing but sigma u hat, and this is a typical eigenvalue problem with the sigma as the eigenvalues. So, this is a typical eigenvalue problem. With sigma as eigenvalues. So, we can come to some kind of analysis. Now, we will be looking into the values of eigenvalues and their signs in order to establish the stability. So, how the sigmas are, so how to obtain the eigenvalues? Sigmas eigenvalues are obtained from the characteristic equation. Eigenvalues are obtained from the characteristic equation, and this characteristic equation will be obtained by solving the determinant of A minus sigma I is equal to 0. We have to solve this determinant is equal to 0, and we will be getting the characteristic equation P of sigma is equal to 0. If it is 2 into 2 polynomial 2 into 2 matrix, you will be getting 2 eigenvalues. It is a quadratic characteristic equation, will be landing up with the 2 roots. If it is 5 into 5 matrix, then you will be getting the 5 roots, a fifth order polynomial of the characteristic equation, and you will be getting the 5 roots. So, whether sigma e to the power sigma t increases or decreases, it entirely depends on sigma. For complex conjugate roots, for complex sigma, the sigma will be occurring in the form of complex and conjugate, and if S is positive, then perturbation grows. If S is negative, then perturbation decays. So, the point is real part of sigma should be greater than 0 for instability and real part of sigma is less than 0 for the stability. Okay. So, stability can be analyzed. So, therefore, stability can be analyzed by looking into by evaluating the eigenvalues. So, stability can be analyzed by looking into the eigenvalues, and let us see how the eigenvalue and the nature of the eigenvalues will dictate the whether the perturbation of the disturbance of the steady state, perturbation from the steady state will grow in time or decay down in time or not. Now, let us see how the eigenvalues are evaluated in this particular case. So, evaluation of if you look into the matrix A u hat is equal to sigma u hat, and eigenvalues are obtained by evaluating this determinant of A minus sigma I is equal to 0. So, if you look into the matrix A is nothing but the Jacobian matrix containing Fc, Ft, Gc and Gt, and these partial derivatives are with respect to concentration and with respect to temperature are evaluated at the steady state. So, these are evaluated at the steady state. So, determinant of A minus sigma I becomes Fc minus sigma f of t, Gc g of t minus sigma is equal to 0. So, Fc minus sigma times Gt minus sigma minus Ft Gc will be is equal to 0. So, if you just multiply this thing, this will become sigma square minus sigma Fc plus Gt is equal to plus Fc Gt minus Ft Gc is equal to 0. So, therefore, we will be having, if you look into the this matrix, what is Fc and Fc plus Gt? It is nothing but the trace of the matrix A, and Fc Gt minus Ft Gc is nothing but the determinant of the matrix A. So, sigma square we can write, we can replace this by trace of A multiplied by sigma plus determinant of A is equal to 0. So, therefore, the coefficient of sigma is nothing but the trace of the Jacobian matrix, and the third term in this equation is nothing but the determinant of the Jacobian matrix. Now, these two equations will be, this equation will be having real root for negative real part of sigma. We can have the condition trace of A should be negative and determinant of A should be positive. Then only you will be having the real negative part of the root sigma. So, if you just invoke how this thing will come, how this condition is come will come, if you remember, for a polynomial a0 s to the power n plus a1 s to the power n minus 1 up to a n is equal to 0, the necessary condition for roots s to be such that real part of s will be less than 0 is that all coefficients must have same sign. So, in this case the coefficient of so therefore, this is positive, determinant of A is positive. So, sigma square is the coefficient of sigma square is positive. In order to have a positive sign coefficient of sigma, trace of A has to be negative. In order to have a positive value of determinant of A, determinant of A has to be positive. So, therefore, these are the conditions of stability for a two-dimensional system. So, trace of A Jacobian matrix has to be negative and determinant of A positive. Both conditions, if these conditions, both these conditions need to be satisfied for having unconditional stability stability of a two-dimensional system. Okay, we can write it as two-dimensional system. For higher dimension system, what will be the condition? That we will discuss shortly. Okay. Now, let us talk about two kinds of bifurcation. One is the saddle node bifurcation. Now, in this case, in this definition, at the bifurcation point, a real eigenvalue crosses the imaginary axis from the left to right, crosses imaginary axis from left to right, and n minus 1 eigenvalues remain on left half plane. Then if this is the case, what happens at this point? A basic steady state becomes unstable, and a new steady state is born, is generated. So, the situation is something like this. You have the real axis, this is a real axis, and this is the imaginary axis, and you will be having, let us say, n number of real valued steady state. For a set of combination of the parameters. Now, for a particular parameter combinations, this steady state starts moving. If we change the value of the parameters, system parameters, let us say this steady state starts moving in the right direction, and for a particular value of steady state, this crosses over from crosses over the imaginary axis and comes to the positive real half plane or the right half plane. So, in that case, that is a saddle point, and at this point the whole solution, one of the steady state becomes positive and the solution becomes unstable from the stable. So, if you one can identify the saddle point by looking into this. So, what is the saddle point? If you look into the equation for the roots of the eigenvalues of a two-dimensional process, sigma square minus trace of A times sigma plus determinant of A should be equal to 0. If you look into the quadratic roots of this quadratic equation, this will be half, sigma 1 2 will be half times trace of A minus B plus minus under root B square trace of A square minus 4 times AC. So, 4 times determinant of A. Now, if determinant of A is equal to 0, let us see what we get. We will be getting sigma 1 2 is nothing but half trace of A plus minus trace of A. So, therefore, sigma 1 becomes trace of A and sigma 2 becomes 0. So, this is the point. So, this is the condition where one of the eigenvalues or the steady state, they becomes one of the eigenvalues becomes 0, and steady state becomes from the unstable from the stable steady state, it becomes unstable steady state. So, one of the eigenvalue becomes 0. What is the condition for one of the eigenvalue to be 0? That is, the determinant of A has to be equal to 0 in order to have a saddle node bifurcation. So, this is the point of saddle node bifurcation. So, the condition is determinant of A should be equal to 0, and by setting this condition determinant of A is equal to 0, one can get the appropriate condition of the system parameters, so that one can get a saddle node bifurcation point and can identify. So, that is the saddle node bifurcation. Next, we talk about the Hopf bifurcation. Hopf bifurcation point for a this occurs for a set of parameters values, for a set of parameter values, real part of complex conjugate pair of eigenvalues become positive, and hence the solution is unstable. Now, if you again plot it on the real and imaginary axis, then we can understand it graphically. Suppose this is the real axis and this is the imaginary axis, and we have, let us say, it is a two-dimensional system. So, we have two eigenvalues which are complex conjugate. Let us say this is one eigenvalue, this is a matching eigenvalue, which of both of them are having the negative real part. So, both the eigenvalues are having negative real part. So, they will be lying on the left half plane. Now, by changing one of the parameters, one can have a, so if we change the parameters, one of these will be moving towards left, another will be moving towards right. So, there may come that for a particular value of parameters, this may cross over the imaginary axis and moving into the right half plane. The point where it moves over the crosses over the imaginary axis and moves to the right half plane, the eigenvalues becomes positive, and the steady state is no longer a stable steady state, it becomes a unstable steady state. So, therefore, if you look into the condition of Hopf bifurcation, if you look into the equation sigmas of the characteristic equation of the coefficient, the characteristic equation of the Jacobian matrix, sigma square minus trace of A times sigma plus determinant of A is equal to 0, and the roots are become 1 by 2 trace of A plus minus under root trace of A square minus 4 times determinant of A. So, sigma 1 2 becomes, one of them becomes 0, purely imaginary, now at this point when trace becomes 0, they become sigma 1 2 becomes plus minus I omega. So, in fact, they will move in the same direction. So, at this point where trace of A becomes 0, then both of these complex conjugate eigenvalues will move over to the from the left half plane and goes to the right half plane, and they becomes one and they becomes they will crosses over the imaginary axis, and the real part turns out to be 0, turns out to be positive. When the real part turns out to be positive, then they becomes unstable. So, the bifurcation point will be the condition when it moves over the left half plane to the right half plane, and the condition is trace of A. So, by setting the condition trace of A, we will be getting a condition on the parameters, so that half bifurcation point can be realized. So, one can get an idea the bifurcation points, the half bifurcation point and the saddle node bifurcation point, and based on that one can get an idea of the combination of the parameters, so that one can land up into the critical points or the bifurcation point. So, in order to avoid the instability in the steady state, one can do away with one can get an idea what will be the bifurcation point and what will be the values of the parameters to be selected. So, one can select the values of the parameter set by the bifurcation points and can ensure that the operator can operate or the plant can be operated at the stable steady state. Next, we will look into the a multidimensional problem. For a multidimensional problem, we have just looked into the stability of a two-dimensional problem. For n-dimensional problem, one can use the Routh-Hurwitz criteria for stability. The characteristic equation in this particular case for an n-dimensional matrix equation becomes a polynomial, maybe S is the root, polynomial of nth degree polynomial. So, this becomes a 0 s to the power n plus a 1 s to the power n minus 1 plus a 2 s to the power n minus 2 up to a n minus 1 s plus a n is equal to 0. This is the nth degree of polynomial, which becomes a characteristic equation of this particular problem. Now, you make a 0 positive. Even if a 0 is not positive, then if it is negative, then multiply both sides by -1 and make a 0 as positive. Then the first test goes like this. So, this is the test 1. Test 1 says that if all coefficients are positive, system is unconditionally stable. System is stable. If any one of the coefficients is negative, there exists at least one root which has a positive real part, and the system becomes unstable. That is the first test. If we will make the all the coefficients in the characteristic equation to be positive, If it has been observed that all coefficients becomes positive, then the system is stable. If any one of the coefficients is negative, now there exists at least one root which will be having a positive real part and the system becomes unstable. So, that is the first test. Then we go to a more detailed test, that is test number 2. This test 2 is that if all coefficients are positive, from the first test, from test 1, we cannot conclude anything about the location of the root. So, we can say that the roots are positive, but all coefficients are positive. From test number 1, we cannot conclude anything about the location of the root. So, for that, to locate the root, one has to form the Routh array. The Routh array is this. We write down the row 1 will be A0, A2, A4, A6, all the even coefficient, row 2 A1, A3, A5, A7 odd coefficients, row 3 capital A1, capital A2, capital A3, A5 like that. 4 will be B1, B2, B3, B4 like that. Fifth row will be C1, C2, C3, C4 likewise. Okay. Then we will be having n plus 1th row will be W1, W2, W3, W4. Now, these are the coefficients of the characteristic equation, then A1, A2 and B1 etc. are expressed in terms of these coefficients. So, we write A1 as A1 A2 minus A0 A3 divided by A1, write A2 as A1 A4 minus A0 A5 divided by A1, A3 as A1 A6 minus A0 A7 divided by A1, we write B1 as A1 A3 minus A1 A2 divided by A1, B2 as A1 A5 minus A1 A3 divided by A1, C1 as B1 A2 minus A1 B2 divided by B1 like that. Now, examine the first column. First column of the Routh array, these will be constituting of A0, A1, capital A1, capital B1, capital C1 like that. Now, conclusion is if any one of these is negative, then at least one root lies in right half plane and system becomes unstable. Number B is number B second interpretation of this Routh array is that number of sign changes in the elements of the first column is equal to number of roots to the right of imaginary axis. So, the condition is that all the elements of the first column of Routh array should be positive for having a stable condition, as well as all the elements in the characteristic equation have to be positive for stable conditions. If we look into the first column, if any one of these is negative, then at least one root lies in the right up plane and the system becomes unstable, and number of sign changes in the elements of the first column is equal to number of roots to the right up plane of the imaginary right up plane or the right up imaginary axis to have the unstable condition. This completes the theorem of stability for a n-dimensional system. So, by using the eigenvalues of the characteristic equation, and the next we will be taking up some of the example to demonstrate the chemical engineering system, this method, how to utilize this method to identify the steady state, and how to test the stability of these steady states and the conditions for the saddle node bifurcations and Hopf bifurcation. Thank you very much.